Hey guys, this is the review for Spiral 14. We're going to start off with some division. And the first guy I happen to notice is a great candidate for some synthetic division. Because we're looking at x plus 2, that means I can put a negative 2 out front. And that gives me 1, 3, 5, 12. I notice that none of those are missing. So I'm just going to perform my synthetic division, bring the 1 down, negative 2. Add, negative 2, add, I get 3, it's a negative, sorry, I can't multiply right now, 6, there we go, and I get 6 as a result. My division step is done. Unfortunately, this is not the answer. The answer, I have to actually put this back in polynomial form. That's my remainder, so that's 6 over x plus 2. I'm just going to write that up there because I ran out of room. Then we have plus 3. Then I have 1x and 1x squared. I increased my degree each time I took a step to the left. For the second one, this is not as good a candidate for synthetic division. I could, but I have to do some extra work, so I'm going to avoid that. Make sure I'm not missing any pieces. 3, 2, 1, 0. Okay, all my degrees are there. What do I multiply 3x by to get to 6x cubed? That's going to be a 2 because 3 times 2 is 6. X squared, distribute that down, and I get 6x cubed minus 2x squared. We're going to subtract, and I get 0. Negative 8 minus negative 2 is going to be negative 6x squared. The most common place we make mistakes is in the subtraction step, especially with negatives. From 3x to negative 6x squared is going to be minus 2x. I'm going to distribute that down. And I end up with minus 6x squared, and I end up with positive 2x. I'm going to bring down my minus x just so I can make sure I'm subtracting okay. And when I go to subtract, we get 0, and negative 1 minus 2x is minus 3x. Bring down my plus 1. To get from 3x to negative 3x, I'm going to multiply by negative 1. Distribute that down, and I get minus 3x, and I get a positive 1. Okay, go to subtract, 0, 0, no remainder. So this is a factor because we get no remainder. Number 2, we're looking to factor these things completely. I see a cubic polynomial with 4 pieces. My first instinct is to try to do this by grouping, because that saves me a heck of a lot of time. I can take an x squared out of the first 2. I'm left with x plus 7. I can take a minus 4 out of the next 2, and I'm left with x plus 7. Woo, that worked. I'm going to take my x plus 7s out front, so I've got x plus 7, and my leftovers are x squared minus 4. That's a difference of 2 squares. So we get x plus 7, x plus 2, and x minus 2. For part B, x to the 4th minus 81, that's also a difference of 2 squares because x to the 4th is equal to x squared, and 81 is a perfect square. That's going to give me x squared minus 9 and x squared plus 9. That's going to go further with the x squared minus 9 because that's another difference of 2 squares. And that would give me x minus 3 and x plus 3. My x squared plus 9 I can leave as is. There's not a good rule for factoring the sum of 2 squares. If you'd really like to know how to do this, and again, we've talked about this a couple times, the sum of 2 squares, you end up with some imaginary factors. You'd end up with x minus 3i and x plus 3i. This is totally okay. You do not need to do this. So not needed. But if you want to know why there's a difference of 2 squares and not a sum of 2 squares, that's why. For numbers 3 and 4, we're looking at the rational root theorem. First of all, I've got to write down all possible rational roots, and then I've got to completely factor this polynomial. Okay. I'm going to do the factors of 24 divided by the factors of 2. So that's 2 times 1 up there, and then for 24, we've got a whole bunch. I'm going to write them down below. All right, so that's plus or minus 1, and that's divided by 1. Plus or minus 24 is going to be the matching one for that. Plus or minus 2, plus or minus 12, plus or minus 3, plus or minus 8, plus or minus 4, and plus or minus 6. This is awesome. I love this many factors, and we're not even done. Those are the ones divided by 1. Now I've got to do all of those again divided by 2. So that'd be plus or minus a half, plus or minus 12, plus or minus 1, plus or minus 6, plus or minus 3 over 2, plus or minus 8 over 2 is 4, plus or minus 4 over 2 is 2, and plus or minus 3. Very thankfully, most of those are repeat factors. I do not need to include 12 twice, for example, or 1 twice, or 6 twice, or 4 twice, or 2 twice, or 3 twice. So most of those get kind of canceled out there. Okay, that's part A, to write down all of those factors. Part B is I've got to completely factor this thing. The first thing that I might do for this is to make a guess that seems pretty reasonable. And for that, I don't know, maybe one of the 3's. So let's try with 3. And we end up with our polynomial 2, 2, negative 16, negative 24. I chose 3 because it's kind of smaller, but maybe in the middle. And that really means I'd be dividing by x minus 3, just to keep that in mind. Okay, let's try this. So we got 2, that's 6. 2 plus 6 is 8. 3 times 8 is 24. Negative 16 plus 24 is 8. 3 times 8 is 24. And we get a 0. That was really nice that I got that in the first try. But again, if you do not get a 0 in the first try, you try again. So what this means is that we get 2x squared plus 8x plus 8 and x minus 3 as our beginning of factoring things. I don't need to repeat the synthetic division again if I get a factor that works and I have something quadratic that's factorable. I might also notice that all 3 of these pieces have a 2. I could factor a 2 out, and that's going to make my life a little bit easier. I also could have done that at the very beginning of this problem, and that would have made me have fewer factors, which would have been nice. And you might notice that this guy sure looks factorable. In fact, it factors into x plus 2, and then we still have our x minus 3. This is fully factored. Part B, fully factor f of x, means this. I don't have any x equals. This is just my factored form. Part C is when I begin to list my roots. Now, my roots, otherwise known as x-intercepts, are going to be anything that makes these parentheses equal 0. So we're going to have x plus 2 equals 0, and that means that x equals negative 2 is one of my roots. In fact, has a multiplicity of 2, because there are 2 of them. And the second part is x minus 3 is equal to 0, which means that x equals 3 is one of my roots. These are my only 2 roots. There are no other terms I can plug things in for. And this is the third step of this problem. I'd like to note that there are 3 distinct pieces. Good guesses, finding the rational roots that might work, factoring, and then roots. Those are 3 distinct things I'm asking for. Number 4, we're doing the same thing. I've got to write my list of possible rational roots, and then I've got to use those to factor. And looking at this, I can tell this is not groupable, so I'm not even going to try that, but checking to see if something is groupable is a great way to begin this. Okay, factors of 10. That's going to be plus or minus 1 and plus or minus 10, plus or minus 2 and plus or minus 5. Thankfully, there are a lot fewer factors for this guy than there were for the previous one. I only have 8 possible guesses here. Part B is I'm going to go about that factoring. I like starting on the smaller side of the middle, so I might choose one of my 2's. and maybe positive 2 to start out with. So we've got negative 1, negative 8, negative 17, and negative 10. Okay, bring the negative 1 down. 2 times negative 1 is negative 2. Add those up, I get negative 10. 2 times negative 10 is negative 20. Add those up, I get negative 37. 2 times negative 37 is negative 74, and this is definitely not what I need. Okay, the positive 2 does not work. Just to close things out, let's talk about the negative 2. And again, this would be dividing by x plus 2, just so we can remember that. So we're going to have negative 1, negative 8, negative 17, negative 10. Negative 1, multiply, and I get positive 2. Negative 6, multiply, I get positive 12. Negative 10, by negative 10, I mean negative 5. A little bit of Freudian slip there, because when I multiply, I get positive 10. And I get 0 as my remainder. So that one worked. I'm going to have x plus 2, and this guy is going to be negative x squared minus 6x minus 5. Don't love that negative. I'm going to factor out a negative 1, so I get negative 1, x plus 2, and we've got x squared plus 6x plus 5. That looks much more pleasant to me because, by golly, that does look factorable. So negative 1, x plus 2, and this is going to factor into x plus 5 and x plus 1. My factoring step, part B, is done. This is the final fully factored form of the polynomial. I would also be okay if the negative 1 stayed in one of those parentheses. That's fine. The last part is finding zeros. And again, this is a different part than factoring. This time I'm going to have 3 distinct zeros. X equals negative 2. I'm going to get another 0 at x equals negative 5. And a third 0 at x equals negative 1. Next step, I'm looking at rational exponents and radical notation. We're going to treat this mostly based on exponent rules. We got to work some understanding of what fraction exponents mean in here. First thing I might do is distribute my 1/2 to each of my 3 terms, and I get 9 to the 1/2. I get a to the 3/10, because 3/5 times 1/2 is 3/10. I get b to the 1/2. I'm just going to rewrite these guys. 2a b to the 3/7. Okay. Second piece of this, I might realize that 9 to the 1/2 is the same thing as the square root of 9. In other words, 3. 3 times 2 is 6. My number part is done. A to the 3/10 times a to the 1. Well, that's the same thing as 10/10. So a to the 3/10 times a to the 10/10 would be a to the 13/10. We add the exponents. Then I've got to deal with my b's. I've got 1/2 and 3/7. The common denominator there would be over 14. 1/2 is 7/14. 3/7 is 6/14. 7/14 plus 6/14, I get b to the 13 over 14. And that is done. For the second part, I'm going to deal with my numbers first. 6 over 14 is going to end up being 3/7. X to the 1/3 over x to the negative 1/5. I'm going to write that 1/3 minus negative 1/5. I'm going to convert that to a common denominator. So that would be 5/15 minus minus is really plus, and 3/15. That's going to be 3/7 x. 5 plus 3 is 8 over 15. You could also have written this as, I don't know why that turned to 3/3, 3x to the 8 over 15 over 7. Second part of this is a little bit easier. We're trying to write this in exponential notation. That's just going to be the base of 6 to the 3/7. This bottom part, the denominator, is going to be the index of the root. Okay? Second part of this, we're trying to simplify. In other words, is there a way to reduce these radicals? And to do that, I'm going to do some factoring. I happen to know that my first guy could be written as the square root of 2 times the square root of 100, and 100 is a perfect square, which is awesome. The second one can be written as the square root of 2 times the square root of 9, and that's also a perfect square. And the third one I'm going to try to write with perfect squares again. 2 times 10, neither perfect squares. How about 4 times 5? That sounds pretty good. So square root of 4 times the square root of 5. Okay? So square root of 100 is 10. First piece is going to be 10 square roots of 2. Square root of 9 is 3. That's going to be 3 square roots of 2. And then square root of 4 is 2 square roots of 5. The first two are like terms that can be combined, so it's 13 square roots of 2 minus 2 square roots of 5, and we are done. In function operations and inverses, we've got a few problems that we have to work through in order to kind of make some sense of this. First thing is to deal with f plus g of 5. I'd like to remind us that this means f of 5 plus g of 5. In other words, f of x plus g of x, and then plug in 5. So let's do that part. 2x squared minus x plus 2x minus 5. And with that, I get 2x squared plus x minus 5. And then if I plug in 5 for x, I'm going to zoom in so I have a little bit more room with these. I'm going to put this up here. Sorry, guys. We end up getting 2 times 5 squared plus 5 minus 5, which is going to come out to be 50. For the second one, I'll go horizontally. F minus g of c really means f of c minus g of c. And all that really means is that we're plugging c in instead of x. So if I were to write this, I could write this as 2c squared minus c, and then minus 2c minus 5. When I combine my like terms, we get 2c squared minus c minus 2 more c is minus 3c, and then minus negative 5 would be plus 5. For the third part, we're looking at fg of negative 4. In other words, f of negative 4 multiplied by g of negative 4. I'm going to do this one in a slightly different order. The other two I added first, and then I dealt with whatever we're plugging in. This time I'm going to plug in first. I'm going to find f of negative 4, and that would be 2 times negative 4 squared minus negative 4. 2 times negative 4 squared is going to be 32, minus negative 4 is going to be 36. And then we find g of negative 4, and that's going to equal, I'm going to go back up to my thing to see, 2x minus 5. So we're looking at 2 times negative 4 minus 5. That would be negative 13. Okay? So fg of 4 means I'm going to multiply these two numbers, and 36 times 13 is something I really don't necessarily want to do in my head, but that's okay. That's going to be 360 plus 90 is going to be 450, plus 18 is going to be 468. And that's my final answer. F over g of 2, I'm going to do the same way. I'm going to write this first by finding f of negative 2. So that's 2 times negative 2 squared. And then, is that plus 5? No, minus x. Wow, that was fun. minus negative 2. And then I'm going to do that out. So we get 2 times 4 is 8. 8 plus 2 is 10. G of negative 2. We're looking at 2x minus 5, I think, for that one. So that's 2 times negative 2 minus 5. Negative 4 minus 5 is negative 9. Then we're going to find f over g. So we're dividing these two. We get negative 10 over 9. Again, it doesn't matter if you plug things in first and then deal with this, or if you set up the problem first and then plug the numbers in before you evaluate. Okay. G of f of 3. All right, I'm going to rewrite these guys because so f of x is equal to 2x squared minus x. G of x is equal to 2x minus 5. So I don't have to keep scrolling up to the top. So G of f of 3 means that I'm going to find f of 3, and whatever the answer is, I'm going to plug into G. So f of 3 is going to be 2 times 3 squared minus 3. 3 squared is 9, so 18 minus 3 is 15. So f of 3 is 15. I'm going to plug that into G. So G of 15 is 2 times 15 minus 5. 15 minus 5 is going to be 10. 2 times 10 is going to be 20. Nice. F of g of x means I'm going to take g of x and plug it in to f of x. So I'm going to write f of x. That's going to be 2x squared minus x. And instead of my x's, what I'm going to do is put in g of x. So that's 2x minus 5 and 2x minus 5. The super fun part here is the squared thing. So that's going to be 2x minus 5 times 2x minus 5, and then minus 2x minus 5. Okay, distributing, we end up getting 4x squared, so that's going to be 8x squared. Minus 20x, so it's going to be minus 40x, and plus 25, so plus 50. Distribute my negative, so minus 2x and plus 5. 8x squared minus 42x plus 55, and that would be our final simplified answer. Moving on to the inverse part of this. You're asked to do a few different things here. The first is to, given a function, find its inverse. That we know how to do. I'm going to rewrite this with y. Because we're dealing with inverse, we know x and y coordinates switch. I can switch my x and y. So 4y plus 5. That's going to turn out to be x minus 5 is equal to 4y. And finishing this up, we get y is equal to x minus 5 over 4. It just reminds me that I don't know that we've really spent much time looking at this notation. This notation means the inverse of h of x. It's about my least favorite notation in math because there's some other things that really complicate that once you get to calculus. But the inverse of this notation you're going to use a lot for some of the stuff we do later this year. Explain domain in your own words. In my own words, domain is the set of all x values that work. So for h of x, which is 4x plus 5, this is a linear function. There are no numbers I can plug in here that don't work. In fact, any polynomial function that you have, the domain is going to be the same thing, which is all real numbers. No matter what polynomial you have, the domain is all real numbers. There are no numbers you could plug in to break it. H inverse of x is going to be x minus 5 over 4. That's another line. Because that's another line, that's going to be all real numbers. okay? The second part of this is explain the range in your own words. Range is something else we haven't really talked about, and there are a couple reasons for that. One is that it's harder to find algebraically, although there is a very simple thing for us to do once we know how to find inverses. And we'll talk a little bit about that in class. So range is going to be the set of all possible outputs, otherwise known as y values. The nice thing with domain and range is that they're alphabetical, domain X, range Y, and that can help you remember which is which. The second piece of this is that since we have inverses, and inverses switch X and Y's, the domain of the inverse of something is the same exact thing as the range of that original function. So if I can find the domain of the inverse, I find the range of the original function. We just did that for these two. Since the domain of h inverse of x is all real numbers, that means that the range of h of x is also all real numbers. The same would be true since the domain of h of x is all real numbers. The range of its inverse would be all real numbers. This is because we're switching our x and y's. And if we're switching our x and y's, that also means we're switching our domains and our ranges. And working with that, you can algebraically find the range of something by looking at its inverse function, if it has one, and identifying its domain.